Good afternoon. First of all, I would like to thank Professor Kurodaleko-san for inviting me to attend this exciting meeting. Earlier, you heard somebody like water. I like baseball. After the Second World War, I was in the third grade. I was told, if you are good enough to play baseball in the team, I did not have to attend the classes in the afternoon. I hate classes. So I played baseball and became a very good second baseman. Well, if you look at the hitting of the baseball, it's the scattering between two hot spheres. So what is important is the impact parameter. For the aiming era, you hit the home run or pop-up or ground ball. What is important is aiming era. So whether you're going to hit pop-up or home run or ground ball. But if two particles is forces operating in between, things will become a little more complicated. So you see, if you see a molecule hit the wall and moving to another molecule or object sitting here, if it is repulsive, it will be bounced backward. On the other hand, if the interaction is attractive, then the molecule will bend over. So in one sense, repulsion will exclude the volume, and attraction seems to expand the volume. And in the real world, you are looking at the interaction between atoms and the molecules. They are at a long distance because of the dispersion forces, fluctuation of charge, electrons surrounding the nuclei. The forces are attractive. On the other hand, when the electron cloud move close together, it will become repulsive. So in the real world, if you look at the atom-molecule interaction, it will look something like this, like helium-2, neon-2, argon, krypton, xenon. And then you look at the scattering process. It is really interesting. If the impact parameter is 0, it will be bouncing back. If you have an aiming error, like become a fly ball, and then become home run, and then gradually it become a pop-up. But because of the attractive forces, pull it in, and repulsive forces push it back. So at a certain distance, the trajectory will come in and go out, and scattering angle will become 0. So if you look at the aiming area and scattering angle, will be moving from positive to 0 and go to negative, going this way and gradually go back to positive. And that's what's happening in the real molecular collisions. And that is really important. If you look at the thermal conductivity, viscosity, or how the gas deviate from ideal gas, all depend on the scattering between atoms and molecules, energy transfers, and things like this. This is important. And if you look at the chemical reaction, again, we know that the collision will bring the chemical change. So if you mix hydrogen molecule and chlorine molecule, it will transform into 2 hydrogen chloride. But as you know, this only shows the stoichiometric relation between molecules. One molecule and one chlorine will transform into 2 hydrogen chloride. But if you really mix hydrogen and chlorine together, there are lots of collisions, but there's no chemical change because it takes a high barrier to induce the chemical change. On the other hand, if you shine the light, chlorine will dissociate, so new molecule will be produced. Sometimes hydrogen chloride could be cold, sometimes could be warm. There's some chlorine and hydrogen left over. If you can follow the trajectory of the atoms and molecule, that's what you might see. You see chlorine dissociate into atoms, and then chlorine atom collide with hydrogen molecule, form HCl. And that's the second step. And then the other hydrogen atom will react with chlorine molecule and form HCl. So HCl produces 2 ways, chlorine atom with hydrogen, hydrogen atom with chlorine. So most of us learning chemical kinetics, we try to understand the mechanism and then understand specific rate constant and then understand how system move systematically from reactant to product. Actually, in the human society, one of the most important chemical reactions is the combustion of hydrocarbon. That's the single chemical reaction providing the energy for our need. More than 80% of the energy coming from this. Of course, carbon-hydrogen bond and oxygen bond is weaker than CO2 or water molecule. That's why the transformation between methane and oxygen will produce the product molecule. As I said, molecular collision induces chemical change, but mixing methane and oxygen, nothing will happen unless you initiate it. So you use the match to start to initiate the combustion process, then immediately you'll see bond rupture, formation of the diamond, elimination of hydrogen, and step by step form the product, end up with carbon dioxide and water molecule. So one of the last important questions is carbon monoxide and OH form a CO2 plus H. So this is the elementary process. Collision between carbon monoxide and the hydroxyl radical will form water and hydrogen. But chemical reaction is quite interesting. Alignment of the molecule is important. So if hydroxyl radical oxygen N is collided with carbon, then two oxygen are happy. They'll become a family. On the other hand, if oxygen bump into oxygen, they'll not be happy. It will be bounced back. So alignment is important. Not only alignment is important, you have to have enough energy to overcome the barrier. So for example, this is the right orientation, but if you do not have enough energy to overcome the barrier, chemical reaction will not take place. 100 years ago, Arrhenius pointed out the specific rate constant depends on temperature, and also rate was determined by how complex the reaction is. This pre-exponential factor A is really determined by alignment factors, and exponential activation energy is really represented in the barrier. And Arrhenius did point out 100 years ago, if we keep on burning fossil fuel and producing carbon dioxide, global temperature will rise. But I don't think at that time he really worried about global warming. He might think that Sweden would be a wonderful place to live, right? Like we will become like California. So now I want to take you through for what I've been doing in the molecular collisions. So as I said, if you look at the chemical reaction, this is the stoichiometric relation, shows the one. So as I said, first thing is you understand the mechanism. In this case, fluorine molecule is a very weak bond, so it will dissociate into atom. Then fluorine will react with deuterium molecule, form deuterium fluoride plus deuterium atom. Deuterium atom will then react with fluorine molecule to form deuterium fluoride. And then this chain reaction will complete the reaction. Actually, if you do it, it will explode. So you have to be careful. But mechanism and specific rate constant will tell you the time dependence of chemical change. But the one thing we really do not understand is the single collisions between fluorine atoms and deuterium molecule, how chemical reaction takes place. So as I said, in the scattering of atoms, scattering of molecule, or scattering of chemical species into product. Sorry, I hope it's better. Okay. You didn't miss anything. The true story will be told now. So what I'm saying is, when chemical reaction takes place, we release energy. Release chemical energy. Weak bond becomes strong bond, where the energy goes. So if you look at the diatomic molecule, if the molecule, two atoms move together, it will be translational. If they rotate, it will be rotational. And then if atoms move against each other, will be vibrational. So the atomic molecule can carry out energy by translational, rotational, or vibrational. And as you know, if you throw the baseball, you can control the speed at any speed you want. A good pitcher from 100 miles per hour all the way down to maybe 70 miles, very slow ball. Electron also, in the infinite space, you can control the energy at whatever energy you want. But tiny little particles with wave nature. So if you confine the motion of particle in finite space, for example, in the pendulum or simple harmonic motion, if particle is heavy, then almost every energy you can excite the simple harmonic motion. But if you have a light particle, wave has to be integer because it's a wave nature, so energy level will be quantized. The reason why energy level is quantized is because wave nature of the particle in a finite space, the quantum number should be integers. So when the chemical reaction takes place, energy go to vibrational will be quantized. That was a dream. I do not think we can see the scattering between atom and the molecule, but we can follow the trajectories. So when I was young, back in 40 years ago, when I was doing postdoctoral research with Professor Hirschbach, there are groups all over the world, in Germany, England, United States, all over the world, people are trying to observe the scattering between atoms and molecules and see the chemical change. And nobody has been able to do it. So all over the world, and I was young, and I do not believe anything is impossible. So when somebody said it's impossible, it really get me excited. So what I wanted to do is to be able to follow the trajectory of fluorine atom colliding with deuterium and what's the deuterium scattering angle and velocity. So if you keep on observing the events, sometimes deuterium fluoride will be moving slower, sometimes faster, even faster than faster. And that is because sometimes energy is stored in vibrational energy, moving very slowly. Sometimes all the energy is translational. So in baseball, just you hit a single, a double, or triple, or you can hit home run. So if you keep on sitting there and observe the product molecule and velocity, hopefully you'll be able to visualize what's going on. So I think time is relatively short. I have to go through very quickly. So in 1967, we started to design the apparatus to try to carry out this experiment. And I did find one thing which was interesting. Everybody said you have to learn from your mistakes, otherwise you will not make progress. But I think it's important to learn from others' mistakes. You really do not keep on making mistakes, you'll not accomplish anything. You really have to learn from others' mistakes. And I try to understand why everybody in the world have not been able to do experiment. And everybody made some mistake. They keep on discussing when molecules collide, the number of molecules produce very small number, and only about 1 million molecules go into the detector, and electron bombardment efficiency is so low. So they said efficiency is low, and at that time, pump can pump to 10 to minus 10 tau. So everybody designed the machine to try to improve the efficiency, but didn't realize that in order to make experiment good, you have to have a good signal to noise ratio, not the signal level. And I did ion molecule relation. I can sit there and count one ion per minute. And 1 million molecule goes through, I can easily produce more than 100 ions. Experiment failed was because background so high. Everybody was building machine with high background. So this machine is specially designed with a triple differential pumping, and second region is embedded, third region is embedded in the second region. So molecule will go, scatter molecule goes through, second region, third region, ionize, quadruple mass spectrometry, meter do ion counting, and scan angular distributions. So all my effort, aside from mechanical construction, is to reduce the background to get good signal to background ratio. This is almost every experiment has the same problem. So sometimes, if you want to select the velocity, we put the velocity analyzer, select the velocity running very fast. So fluorine molecule dissociated with a Maxwell-Boltzmann distribution. I want to pick up a certain velocity and collide and scan angular distributions. And I just want to show you what the inside of the machine looks like. This machine is rotated. And we have some other gadget to reduce the background. I don't think I have time to go through it. And that's the first time we measure scattering between neon and neons, neon and neon scattering. And when we published the paper, everybody was astonished. Gee, I thought it's impossible to do this, but we did build a machine to do it. And you look at the argon-argon scattering. Those are differential scattering cross-section. From here, you can derive the potential, and if you know the potential, you can carry out all the calculation of the transport phenomena. As to the chemical reaction, fluorine atom and collide with deuterium molecule and produce deuterium fluoride. We scan the velocity, angle, and that's the contour map. It means at low energy, fluorine and deuterium has to line up together. Deuterium fluoride produce energy are mostly carried away in vibrational energy. And the ability of observing single collision or you isolate the molecule to look at the dynamic of dissociation or doing spectroscopy is really quite important. I don't have time to go into detail, but I do want to come back to the question of Professor Nerdy raised, where do we come from? Well, he came from after the war. I'm a couple years older. After the war, I trained baseball. But when I say where do we come from, I want to start from the creation of solar system. That was 9.5 billion years after the Big Bang. And 1 billion years after the creation of the solar system, phenomena of life started on the surface of the Earth. And after 4.5 billion years, that's what we are. That's the Earth we live. 2 million years ago, our ancestor appeared. And gradually, only one species, Homo sapiens, occupied, really spread all over the world. And that's the Earth we live. We, Homo sapiens, the number are so small, didn't really impact the global environment that much, except when we have an industrial revolution after invented steam engine, weaving machine, and all of those, then we change. This is the painting of 300 years ago, Aboriginal tribe in Taiwan. This picture, I just want to show everything from the housing and the carrier, bride and bridegroom is carried by 4 people. Everything is from biomass. Everything was given by sunshine. But after Industrial Revolution, what happened? Everything we see, concrete, steel, all dug out from the ground, in fossil fuel to transform it. So we used to be a part of nature, and gradually we feel we are the master of the nature, and that dissociation, departure from nature is really causing lots of problems. And Dr. Nerdy did mention tremendous progress in this technology, science and technology, from 1850 until now. But the amazing thing is, along with the technological advancement, we are burning the fossil fuel in higher and higher quantities. And this is at 208. Biomass is very small. Most of the energy we consume are from coal, petroleum, and methane. And that development, along with the population explosion, at the beginning of the last century, we have 1.5 billion people. At the end, we'll be 6.6 billion people. Now we have 7.2. By 2050, United Nations is estimated to have 9.7 billion people. And with the population and consumption, we have overloaded the Earth. We have really overloaded the Earth and changing the global environment. So that's the society we live now. And you heard about free trade, globalization, and you look at the free trade and globalization as a human society, you look all over the world, you are seeing people are seeking global cheap labor. Used to be Asia provided cheap labor. China, now go to Vietnam, Indonesia, provide cheap labor and natural resources and crank through and produce consumer junk. I'm sorry to say it's junk, but we are using a lot of language unnecessarily. And we have destroyed the environment and pollution and CO2 emission keep on going up. And somebody had all speed ahead. GDP is increased by 5.3%. And that's the world we are in. Whether you like it or not, that's what we are doing. It's horrible things. And Yuan Tseh like to say that the planetary boundary, we are exceeding planetary boundary. And we are in a very precarious position. We are in bad situation. But if you look carefully, we are living in a very thin layer above the Earth. There's a hydrosphere, atmosphere, geosphere. We are living in these thin layers. For 20,000 years, it's called Holocene. The natural process is such that climate was stable. Carbon dioxide is about 280 parts per million, but it is increasing. We are changing the environment. The first thing you will notice is the air pollution. You go to many major cities in Asia, China, India, and if you want to convince me that's the progress. Do you believe it? Is that the progress? You're suffocating yourself. I do not believe it's really progress. But second thing, which is the most important thing, is the energy balance. Sunshine provides us energy, and we are emitting energy to the universe. And if there's no greenhouse gases, the carbon dioxide, methane, our temperature might be minus 20 degrees. But before Industrial Revolution, carbon dioxide is about 280 ppm. Temperature stable, quite comfortable. Now, because of the greenhouse gases is increasing, we are trapping more energy than we're giving out. So temperature is rising. So if you look at this, summertime is low, winter is high, but carbon dioxide concentration from 1980s keep on going up. The blue color is on the South Pole in the opposite end from Mauna Kea, which was measuring. So summer is up high. You see, by 2000, you already go to 370. It's up, going up, keep on going up. And now we are reaching 4,000. It's reaching 4,000 and keep on going up very fast. And that's really quite horrible. If you look at the time before Industrial Revolution, it maintained around 280 ppm. You do go through the glacier period because the Earth orbiting is not wrong, and self-spinning of the Earth is making an angle with the orbit. So there's a glacial period that will go through maybe 20,000 years, but never been so high, but we are right here. And when the carbon dioxide concentration equivalent go to 450 ppm, temperature will rise 2 degrees centigrade. That will not acceptable. So here we are. Then the last year, there's a COP21. People got together and said, it's not good. We have raised the temperature. This here said 0.61 degree. It's not right. It was now at the present time it's more like 0.8. But last week, Jim Hansen published a paper. The care analysis showed that we've gone up 1 degree already, 1 degree centigrade. And then it would be miserable if we allow the temperature to rise 1.5 degrees before pre-industrial era. So we have only very small margin. And actually, if you look at the IPCC report, and here is the pre-industrial era. Everything's white color. It means everything is pretty good with a unique threatening system, extreme weather events. But now, actually, it's really up here, high. So if you look at it here, it's in orange color. Extreme weather events, it is really quite serious already. We are on the Earth, extreme weather event is getting serious and serious. And the most worrisome thing is large-scale singular event might wipe off large fraction of human society is getting pretty bad. So we keep on saying, keep the temperature 2 degrees centigrade. That's irresponsible for the younger generation because 2 degrees centigrade world is really horrible. That's why COP21 said 1.5 degree, 1.5 degree. And if you don't do anything, temperature go up to 4.5 degree. That's the world I don't think is really livable world. So that's what we are facing. We are facing temperature is rising to 1 degree and only 0.5 degree. And we can dump no more than 1,000 billion tons. We are dumping 50 tons a year. 20 years, we reached that. 20 years, we reached the horrible time. I said we are in a horrible situation. Like you look at the Yolanda typhoon, Haiyan typhoon, landing speed, maximum speed is 100 kilometers per hour or 100 meters per second. In one sweep, 7,000 people killed in one sweep. And that is something is happening. So COP21, leaders in the world got together and said, we have to deep decarbonization, and concluded that the non-binding agreement to move toward the 2 degree centigrade limit, and then said, and ideally to a 1.5 degree centigrade limit, because scientists will tell you 2 degrees centigrade is miserable. We really have to keep ourselves at 1.5 degree centigrade. Other thing is we transfer $1 billion a year to help developing countries by 2020. That's an easy part. Because global economic activity is a tune of $100 trillion. This is 100 billion. It's a tiny little amount of money, one part of 1,000. And by 2020, we'll revisit carbon reduction plans in 2020. So what I'm saying here with you is we are in a very horrible situation, and none of the politicians are committed to do things to save the next generation. Professor Claude Alejo and I served in the International Council of Science for many years. That's the organization said promoting international science for the benefit of society. But we know we are heading toward the disasters. And people talking about economic growth. And Professor Noemi also said, we're always talking about technology. But young people say, do something, you bunch of maniacs. And the older generation say, well, it's easy to just criticize young lady. And I suppose you've got an alternative all work out. Have you? Historical eco-fanatics, always telling people how to live, get yourself a proper job, and then without knowing it, half a century, we'll be all go down together. At the time, I will not be there. So I always said, young men, young women, do not trust the older generation. Always try to tell you what to do, and it will not be their decision making, should not be theirs. Now, I want to summarize it. Politically speaking, this is a global problem, need of global solutions. But United Nations is nation-state based. Every time we said nations should do this, we didn't have a mechanism to work together yet. And also socially, if we have too many people consume too much, overloading the earth, we are by definition overdeveloped. In an overdeveloped world, nobody in the overdeveloped world should tell the not yet overdeveloped world that's the way to go. I think not yet overdeveloped world should find a way, different way to develop, and overdeveloped world also has to turn down. Technologically, today, transformation from sunshine to electricity is very inexpensive, but we have not learned to store those electricity to make it available in the global market yet. So that's a technological problem. We must learn to store, transform, and share energy from the sun. But I'm sorry to say that what we are doing are not doing right. We don't have bright future ahead of us, and we have to work hard. Work hard. First thing, we have to decarbonize our society. By 2050, we have to become carbon neutral. Every scientist is doing everything they can, but we have to come up with a total picture, carbon neutral by 2050. That will not depend on science technology alone. We have to reorganize the society, we have to change our habit, but we have to do it. Otherwise, we'll be very sorry. And there's no excuse for the current generation to bring the earth to such a bad, horrible state. Well, thank you very much.
Thank you very much, Dr. Lee. So now I move on to the question time. And we will first welcome the questions from students who have not asked question yet today. So please line up behind the microphone. Yes, please.
Thank you for the wonderful presentation. And I have a question to you. You mentioned that you measure angles and velocities to visualize the molecular collision.
Mm-hmm.
But I wonder whether or not it is possible to do the same thing using the supercomputers.
Yes, certainly. I think in 50 years ago, when I did helium scattering, computer cannot, theoretical calculation cannot come up with a reliable interaction potential, and they didn't even know that helium-2 is a bound state or not. But nowadays, you don't have to do helium experiment. You can do the calculation and carry out even the fluorine plus hydrogen molecule. You can carry out the calculation and tell you what's going on. But supercomputer certainly brought us in a very different stage at the present time.
Thank you.
Thank you. So next question, please.
Thank you for a great presentation. About new energy, I am interested in methane hydrate. However, if we take methane hydrate, there may occur underwater landslides and promote global warming.
Yeah.
However, methane hydrate has enormous possibility, and so shouldn't we get it and use methane hydrate which we newly discovered?
Well, if we want to decarbonize human society, then we will depend on sunshine. Sun will give us enormous amount of energy is more than enough. In 1 hour, the amount of energy sound transmitted to the surface of the Earth is about equivalent to the energy we use in the human society in 1 year. So methane hydrate, although it has lots of energy, we better not burn it. But what people worry about, the methane hydrate, is when the ocean warms up, methane hydrate might start to bubble out. In year 2000, Professor Nishizawa Junichiro wrote a book and said humanity will be perished in 80 years. And one of the things he worried about is the methane hydrate. It will bubble out from the ocean. So it's not a good thing to use the methane hydrate. We have to learn to store the electricity or transform it.
Okay, thank you.
Okay, thank you very much.
So next question, please.
Thank you for a very good lecture for us. I'm really inspired. And I think you said in the presentation that we young people has to research for the technologies for the next generations for a sustainable lives environments.
Yes.
But I've heard of someone or opinion that says the research that kind of things also threats the environment too.
Yeah.
How do you think about that kind of opinion?
Yeah, this was the people was talking about light and shadows of science and technology. I think the science and technology caused the human society to develop. But then we found out that with so many people, Earth become finite, and we are changing the environment. So I participate in many international organizations about science and technology, keep on giving people a promise. The science and technology will make this place better. But without looking at the entire world and said, actually, the science and technology, without knowing that we have a boundary condition to satisfy, then we'll be really going into the negative direction. So application of science and technology, one has to be careful.
Thank you very much.
Thank you. Next question, please.
Thank you for your lecture. It was very interesting. There are some scientists that assert that global warming theory is not true, and they claim that the recent global temperature rising is not due to the human activity, but it is due to the fact that global fluctuation of global temperature is on the cycle, and the modern time is the time that the temperature should be rise. If you think that the recent temperature rising is due to the human activity, what do you think the flaw of the assertion is?
Well, in the slide I did show that you trace back the time backward. Then you do see glacial period every 20,000 years. And that is the so-called fluctuation of temperature, because Earth moving around the sun is not circular.
Yes.
And also the spin is making an angle. So for a certain period, it will go into ice period and glacial period. That will come. But the time is in thousands of years. So people say, Professor Lee, you wait. The glacial period will come. I said, how long are we going to wait? In 50, 100 years, we're going to wipe out the humanity. How can you wait for 2,000 years? And also, when we change the global environment, and in winter, snowfall or ice will not be formed, the reflectivity also will change. And entire system will move from one state to the others, and waiting for Earth to cool off. This is almost impossible. Scientists will tell you, sea level rises is irreversible now, and at the end of the century, it is a multi-meter rise, whether it's 1 meter or 2 meters, depending on how we do it. And it's not, we do not have certainty. But sea level rise and things like this, it's not reversible anymore. So scientists did study every detail, and although some of the fine detail might still need to be investigated, but energy in and out and global surface temperature rise, there's no question anymore. That's why politicians came together in COP21. They realized it's important. But they will not be in the position 4 years later anyway. So that's the main problem.
Thank you.
Next question, please.
You talked a lot about how Earth has limited energy we can use. What do you think about nuclear power as alternative to all the other power that combust something as way to fight our environment depriving natural resources?
I didn't quite understand what you said. You said,
So what do you think about nuclear power as way to fight depriving natural resources?
I think if you look at the current nuclear technology, it was developed more than 50 years ago. And at that time, people worry about proliferation of weapons. And the current nuclear technology, from my point of view, is not a very ideal energy source. We burn about 2% of the uranium fuel, and then 97, 98% become waste. So that's really not an ideal situation. If we work together, every country work together, and come up with a next generation of nuclear energy that will burn everything, will not produce waste, and then you don't have the problem of weapons proliferation. And it's not impossible. Like some of the people many years ago worked on the molten salt reactor. Ideally, they will burn thorium toward the end. So nuclear energy, if you think about the decommissioning of nuclear power plant and take care of nuclear waste, it's not really a good option. Especially sunshine is abundant, and we already learned to transform sunshine into electricity so efficiently now.
Thank you very much.
Thank you. So it's time to close
Yes.
this session. So thank you very much, Dr. Lee.
Thank you.